Hello everybody, how are you people? So we are back again with a very new session and today's topic is thermal properties of matter and heat transfer. Okay, so this is going to be a very nice session guys, but jaldi मुझे बताओ तुम में से कितने लोग chat में हैं? How many of you are there and am I audible and visible to all of you? In a moment or so we'll be starting the session. The session will be very interesting. Obviously we'll be talking about all the thermal properties of matter and then there will be a discussion about calorimetry, then also how transfer of heat occurs. So there will be a very good discussion. बहुत ही इंटरेस्टिंग सेशन होने वाला है, तो आप लोग जल्दी आ जाओ. जितना भी आपका काम है जस्ट कीप इट असाइड एंड कम ओवर हेयर. हम बहुत ही जल्द सेशन स्टार्ट करने वाले हैं. ओके एंड अगर मैं इस चैप्टर की बात करूं, थर्मल प्रॉपर्टीज ऑफ मैटर, सो it's a very good chapter and a bit confusing as well. So many students face difficulty in this chapter and इससे questions की अगर बात करूँ तो near about 2 to 3 या किसी साल 1 question, you might expect these many questions from this chapter. And the best part about studying this chapter is there's a topic in it, conduction, जिससे maximum questions आते हैं and that is very relatable with electric current. So if you all know वेरी गुड इलेक्ट्रिक करंट कैसे ट्रांसफ़र होता है वहाँ पे करंट का, how resistance is calculated over there, then you can very well relate it over here and I'll be telling you a very good approach as well how to solve questions whenever there are questions of conduction or any heat transfer questions are also there. So there's going to be a वेरी नाइस डिस्कशन. मैं आपको बहुत अच्छी ट्रिक्स भी बताऊंगा जिससे आप आंसर भी बहुत ईजिली निकाल सकते हो. ठीक है? ओके, सो लेट मी गिव यू अ ब्रीफ अबाउट माई सेल्फ. सो माई नेम इज आदर्श राय एंड आई एम अ ग्रेजुएट फ्रॉम NIT Bhopal. And if I talk about Extramarks, so it's quite obvious we have a very good repo in the JEE NEET market and we have ensured that out of every 7 candidates, one has been selected in JEE Main. Okay, and they are presently getting studied in their colleges as well. So we have a very good and a brilliant team of IITians and NITians though who actually are expert in their stream. They already have qualified this exam with a very good rank and presently they are just in service for you people, जिससे आप लोग भी अपनी preparation बहुत ज़्यादा easily कर पाओ. You can also achieve those ranks which they have already done. Okay, so let's move ahead and we have our app, the description to which you can the link to which you can find in the description. You can just go for it, click it. दोनों ही प्लेटफॉर्म्स पे आपको वो ऐप मिल जाएगी एंड द रीज़न वाई आई एम टेलिंग यू इज़ दैट बहुत ही अच्छा इंटरफेस है आपका. यहाँ पे बहुत अच्छी तरीके से सेगमेंटेड हैं. आप लाइव क्लासेस भी देख सकते हो, आप क्वेश्चंस भी सॉल्व कर सकते हो, आप टेस्ट भी दे सकते हो. सो all the things which are required from the point of a student who wants to clear an exam are all under this single roof only. So you don't have to travel here and there or listen to here and there. These sessions, even these crash course sessions, can also be viewed using the application itself. So do download it. जिन्होंने भी download नहीं किया, do download it. You will definitely love it. Questions बहुत अच्छे से segmented हैं and questions are not random. Okay, questions are actually on the basis of what has been asked in the previous years. उसको सिंक में रखते हुए ही वो questions segment किए गए हैं. आप टेस्ट सेक्शन में जाओगे और टेस्ट में अगर आप ट्रेंडिंग टेस्ट या स्कोर बूस्टर टेस्ट देखोगे या फिर जो भी टेस्ट सीरीज चल रही हैं वो सारी चीज़ें देखोगे, सो यू विल डेफिनेटली नो कि किस तरीके से वो टेस्ट प्लान्ड हैं. आपका डेफिनेट इम्प्रूवमेंट होगा. ओके, ठीक है. एंड साथ ही साथ टेस्ट के बाद आपको एक बहुत अच्छी एनालिसिस रिपोर्ट भी मिलती है जिसमें यू कैन वेरी वेल नो इन विच क्वेश्चंस आई वाज वीक, विच क्वेश्चंस टुक मी अ लॉट ऑफ टाइम एंड व्हाट ऑल वीक एरियाज डू आई स्टिल पोजेस सो दैट आई कैन वर्क अपॉन देम एंड एलिमिनेट देम. ओके, now let's move ahead and talk about this chapter of heat and temperature. So what it is and sir 10th में हूँ, IIT के लिए कौन सी book prefer करूँ? Okay, so what your name is I cannot get it, but books की अगर मैं बात करूँ, so there are so many standard books in the market. You can actually refer them and there's no one name. There are so many, but the problem with them is that it's not properly segmented. Okay, so exams are changing, the pattern of questions which are being asked are also changing. So books are not that dynamic in nature. Okay, but an application is. So that's the reason I am stressing on you to download the app, because those questions which are over there, those tests which are being created by us, they are especially created by keeping in mind the questions, the pattern, the hot topics of all these chapters. So say suppose I talk about heat and temperature or transfer, heat transfer. So from which unit or which concept most of the questions have been asked. So the questions have been created and put in up on that keeping those things in mind only. So that is the reason I was telling you, and if you are in 10th, this is the best time. You can actually kickstart your preparation for JEE. Okay, you can actually just cover some questions of 11th, and thereby see what happens is when I was also in 10th, I actually was at trouble when seriously I just saw that huge syllabus of 11th physics, chemistry and maths, because I wasn't used to it. So during I always felt that during my 10th also I got a lot of time. I could have just covered some concepts of 11th which could have actually helped me, because there's a transition whenever a student goes from 10th to 11th. There are so many new things occurring in his life, and along with it, so huge syllabus also comes into action. So sometimes just looking at the view of that syllabus only, we just back off, irrespective of the fact that we could have cleared the exam if we were given a very good and a right approach. Okay, so work upon things, try app download करो आप, एंड ट्रस्ट मी ऐप आपको एक बहुत ही अच्छा इंटरफेस मिलेगा जहाँ पे आप यू कैन जस्ट एक्चुअली फाइंड थिंग्स वेरी सेगमेंटेड. अच्छे से आपको अलॉन्ग विथ योर कैटेगरी कुछ फिल्टर्स लगा के डिपेंडेंट अपॉन योर क्लास, अपॉन योर टॉपिक्स, यू कैन एक्चुअली फाइंड गुड क्वालिटी रेलेवेंट क्वेश्चंस. इंस्टेड इवन यू कैन अटेंड लेक्चर्स एज वेल, जैसे कि क्रैश कोर्स हो रहे हैं, यू कैन अटेंड दीज लेक्चर्स एंड आप अटेंड करोगे तो यार ऑब्वियसली यू विल have a takeaway element in it, and more than that आपका revision हो रहा है. You will better know कि okay, have I learnt all these concepts or not, or still something or the other is missing. You can cover up from these lectures. Okay, and mostly these lectures are free of cost, so you don't have to pay a penny. So it's just your time which we are asking you to invest. Okay, so with this note, we'll be just beginning our session, and the first topic which we are going to discuss is about heat and temperature. So people normally confuse between heat and temperature. What it is? So heat is actually energy. Okay, and temperature is a physical quantity. If you remember the fundamental quantities, so temperature was one amongst them. So temperature, we measure temperature of a body, that's its intrinsic ability. Actually it depends obviously on the motion, the randomness, the motion of the molecules of any gas. So increasing temperature, the motion also increases, and decreasing it, the motion also decreases. So temperature is a quantity of a material, and based on that quantity heat energy travels. So the energy which is transferred from a hot object, obviously with a higher temperature, to a cold object due to temperature difference is called heat. So you can relate it with the presence of pressure difference, air flows. So air always flows from a higher pressure to a low pressure, and that is the reason behind winds which we are observing on a daily basis. So all the winds on coastal areas or anywhere in middle India, so all those winds are occurring just because of the pressure difference. So if there isn't any pressure difference, then no amount of wind will flow. And that is also one of the causes for air pollution, because air and the pollution particles getting accumulated over there, they are not allowed to move from one place to another because of the absence of winds, and hence the pollution is also increasing. If they readily move from this place to that place, then obviously the air gets rejuvenated and the pollutants will be decreased. So just like that, in sync with that, whenever there is a temperature difference between 2 points or 2 objects, there always will occur a heat transfer, and obviously the heat transfer will be from higher temperature body to a lower temperature body. Okay, cool. Yeah, the reverse of it occurs in the case of a refrigerator. So how that mechanism is working, stay tuned for the thermodynamics lecture, so which will be occurring in the coming days only. And if you haven't subscribed this channel, just subscribe it, because you'll be getting regular updates about the classes, about the next few chapters which are going to occur, or in physics, chemistry, maths, whichever topic you wish for. So the alternate to it also occurs, but an external work is required. Okay, and extra energy has to be given, and the case happens in a refrigerator. Okay, and even an AC, air conditioner. So what they do, they actually extract heat from a cold environment and transmit it to a hot environment. Okay, so this is the natural thing, this is the natural flow, that always heat will flow from a higher temperature body to a lower temperature body. The SI unit is obviously joule. When there is one more very popular unit, that is calorie, and 1 calorie is near about 4.2 joules. Okay, always whenever you get a question in calorie and you are asked to find the answer in joules, then always remember that 1 calorie is near about 4.2 joules. Hi Arpit, how are you? Hi Vignesh. Okay. So now let's move ahead and talk about temperature. Yes, temperature, the physical quantity which actually gives you the measure of how cold or how hot a body is. So it is a measure of the hotness or coldness of an object. Okay, two bodies which are in thermal equilibrium are said to have equal temperatures, obviously, if the heat isn't flowing from one body to another. Okay, so what happens is that suppose it's a summer day and it's very somewhere you are located in central India or northern India, and during summers the temperature is around above 40 and you are in your air conditioned room, and what happens is you just go out and you बहुत ही जल्दी आप लोगों को feel करते हो यार it's very hot. The reason is that heat energy is actually flowing from a high temperature that is surrounding inside your body, because you are actually not of that temperature, your body's temperature is not above 40. So but after some times you feel okay, and for the initial few seconds or few minutes or few hours you feel very hot. Okay, so that hotness or coldness which you are feeling is just because there is an energy transfer, and after some time you feel okay. So the reason is that now your body's temperature is actually very close to surrounding temperature and you are in thermal equilibrium with the body, and there is no heat transfer occurring between you and the surrounding. And this is what the statement says is when two bodies are in thermal equilibrium, there is no heat exchange between them, because obviously both of their temperatures are same. So heat transfer requires temperature difference, and if there isn't, then there won't be any heat transfer occurring. Okay, so this is what thermal equilibrium is all about. Now let's talk about the very famous expansion. What expansion is? So what happens in expansion is, this is a very normal phenomena, and we actually, all the engineers, all the constructions are occurring keeping this expansion in mind. So we staying in India, we are a tropical country and we actually face a huge range of temperature variations. So we have points in Himalayas wherein the temperature is around minus 12, 20, okay, and we have places in India only where temperatures go above 40, 45, 48 even, okay. So we are a country where temperature varies a lot, okay, and since the variation is of that big amount, around 40, 50 degrees centigrade, so what happens is things expand in summers and they used to contract in winters, okay, and the amount in which they are expanding or contracting, we need to actually take that into account before constructing any objects. So this is a very common case study, so many of you must have heard about it, that during the construction of rails, whenever rail lines are created, a small amount of gap is actually placed between two rail lines wherever the joint is occurring. And the reason to this is only that during summers that small gap gets filled up because the rails expand during summers, and obviously during winters they contract, and you can very well view that particular gap between two rail points. So whenever two rails are to join, they are joined using some nut bolts and all, but there's a particular amount of gap, okay. This gap which I am talking about, there's a gap which gets filled up in summers, they come close to each other, and during the winters it's easily observable. So this gap is actually present just to avoid the presence of or the creation of thermal stress. So suppose there isn't any gap between those two rails, so what will happen, they will want to expand during summers, but you're not allowing them. So what will happen, a stress will get developed, and because of that stress, eventually as the train moves, that fatigue can occur, and even the breakage of the rails can occur, and very serious happening can occur. So just to avoid that, this thing occurs, and the reason to this is that expansion occurs in bodies whenever temperature is raised. So expansion also occurs in three fashions, and those three segments along which expansion is occurring is based on the dimension. So if the expansion is occurring in linear or one dimension, then we term it to be linear expansion. If it is occurring in two dimensions, suppose I have a plane body, if I have a rod, then obviously I will be expecting the expansion to be majorly occurring along the length only. But suppose now I have a square, I have a two-dimensional plane, I have a square, I have a circle, then the expansion will occur during both the axes along which that object has been placed. And if it is along 3 dimensions, then it will be termed as volumetric expansion, and expansion will definitely occur over there as well. And the expansion which occurs, the change in length, will obviously be dependent upon some parameters. And what are those parameters? So you can just look it over here. So suppose I am talking about linear expansion, and delta L has been represented as L alpha delta theta, where delta theta is the temperature change. So obviously the change, the expansion occurring will be directly proportional to its original length. So if we have a rod which is quite long, then the expansion will be more as compared to a rod which is lesser in length. Okay, and it is obviously more proportional. It is proportional to the change in temperature even. So if the temperature change is not that huge, if the temperature change is obviously not that huge, as in the case if we go at equator, so the temperature or in a coastal region, so in a coastal region the temperature variations are not that huge. So there the expansion you might not occur, or you might not notice, because the temperature range, the amount of temperature variations which occur will actually have a significant amount of effect on the change in length which is occurring. And one more thing is coefficient of linear expansion. So this parameter, the coefficient of linear expansion, actually inculcates the material property. So some material might expand a lot, but some materials might not. So this alpha will actually tell you the material properties. So overall what I can deduce is that the delta L will be directly proportional, and even not directly proportional, will be equal to L alpha delta theta. Okay, and this delta L now can be replaced by final length minus initial length. Okay, and that this can be replaced by final length minus initial length, and this will be obviously equal to initial length into alpha delta theta. Okay, this Li will go over there. So finally what you will have is that length at any temperature will be equal to initial length 1 plus alpha delta theta. Okay, and on a similar approach we have the coefficient of superficial expansion as well as beta, and the expansion will be equal to a theta will be equal to a naught 1 plus b delta theta. And similarly if I talk about volumetric expansion, then over here as well the volume at any theta will be equal to v naught, that is initial volume, into 1 plus gamma delta theta, wherein alpha, beta and gamma were what? They were coefficient of linear, superficial and volumetric expansion. Okay, then if volume is increasing, say suppose volume is increasing, and can mass increase? No. For extra mass you will obviously have to put in more amount of the substance. So we are not putting or removing any mass from an existing mass. So mass remains same. So if volume is increasing, then density has to decrease. Okay. So if volume becomes more by delta V, then density will definitely reduce by an amount delta rho, and the expression is mentioned over here. Only the change which will occur is that in place of V, we will have the density at any theta will be equal to density at the original point wherein no expansion was occurring, and then there will be 1 minus gamma times delta theta. Okay, because as obvious, I told you, if volume is increasing then density has to decrease, and on the other hand if volume is decreasing then density will obviously increase. Okay. Hi, I am a student of yours on Extramarks. Okay, I am very good, I am very nice, and it's good to know you are a student of Extramarks. So attend these lectures and just tell us if you're liking it or not. अपने दोस्तों को भी बुलाओ यार, all those friends of yours who are actually in dire need of these lectures. They must be looking at so many lectures here and there. देखो, it is never about how much amount of knowledge you have, or you should always have the knowledge which is required at the moment. Okay, and at the moment you should have a knowledge which should be specifically targeted for JEE Main and Advanced. Okay, if you are learning some concepts very deeply out of your interest, but that's not going to help you. That could be understood, that should be learned, but when you get a free time, okay, and if you're bored with your studies, but your approach should be very streamlined. Okay, you should not just mug up things from different sources, and it should be very streamlined. Just trust me on that, because I've seen so many students who were very good. Actually, they had very good analytical abilities as well. They can think of that. See, these questions, these entire concept is actually to make you people develop those analytical abilities. Okay, what should an engineer should have? So what happens to an engineer is that he is given with the circumstances and he need to find a way out of it. Okay, and that circumstances are never ever repetitive in nature. There could be some different circumstances. There could be some different circumstances. Okay, so you need to know the process, or the you should have that analytical ability in your mind such that you can just streamline those things, or you can create a positive result out of those random data. Okay, so these lectures, these entire things are all just for you only. Okay. Now let's move ahead and talk about thermal expansion, actually the relation between coefficients of linear, superficial and volumetric expansion. So what happens over here is, suppose we have an isotropic body. So what happens in an isotropic body is, if the temperature has been increased, its entire dimensions along x, y and z, they will expand in an equal proportion, and that's an isotropic body. If I talk about an anisotropic body, then the expansion is very random. Okay, so if we have an isotropic body, then its linear expansions coefficient, volumetric and superficial expansions coefficient have a relation between them, and the relation is this, that alpha will be equal to beta by 2 and that will be equal to gamma by 3, or conversely you can also say that gamma will be 3 times the coefficient of linear expansion and beta will be 2 times the coefficient of superficial expansion. Okay, so just keep this in mind, because I've just noticed a question based on this, because it was obviously discussed in one of the webinars as well, that the question was asked about find the coefficient of volumetric expansion, and the data given to us was somewhere which could have just projected the result of linear expansion, and thereafter that we had to remember this formula. It wasn't given to us as isotropic body, but or if we wouldn't have assumed it to be an isotropic, then the result would not have arrived. Okay, so from the data given to us we could have only found out the value of linear expansion, but what was asked? They were asking about coefficient of volumetric expansion. So we should be knowing the relation, how these coefficients are related with each other as well. Okay, so now let's move ahead and talk about this anomalous behavior of water as well. So you all must be noticing or must have heard that there is one more anomalous behavior with water. It's whenever we solidify water, so solids, any material if you take, there is a solid, there will be a liquid and there will be a gaseous state. So the solid state will obviously more denser than water, but in the case of ice, its density is actually lesser than water. Okay, and regarding density of water only, so there is an anomalous behavior, and the reason is that at 4 degrees centigrade, water has its maximum density, and the density will be reduced below that 4 degree, matlab between 4 and 0 degree as well, and after 4 degree as well. And since density has a maximum value over here, so volume will have, suppose you have taken a mass m, okay, you have taken a mass m, and that mass m will obviously not change unless and until you are adding or removing some amount of water from it. So if density is changing with temperature, then obviously volume has to change, it has to reciprocate accordingly. So volume for a given mass, volume will be least at 4 degrees centigrade and it will be maximum at any temperatures higher or lower than that. Lower till 0 degree obviously, because then the state changes, and higher till 100 degree, and obviously after that the state changes. And one more thing, I'll be discussing about specific heat capacity as well. So water has that brilliant amount of heat capacity. That means a particular mass of water if you take, and particular mass of oil and so many other things if you can take, the maximum amount of energy which can a material absorb in response to the increment in its temperature, you have water out of there. Okay, so in so many nuclear power plants we use water, hard water, to actually absorb that excess amount of energy, because it has a very great heat capacity as well. Okay, and I'll be discussing about that, don't worry. So for water, gamma is negative between 0 and 4 degrees centigrade. Gamma means negative. What do you mean by gamma is negative? That as the temperature is increasing, volume should increase, right? As the temperature is increasing, volume should decrease, but on the contrary what you will observe is that its volume is decreasing. Okay, so this is what this entire case is pointing towards, and obviously on increment of temperature the density should decrease, but between 0 and 4 you can see is the density is increasing. Okay, it is not decreasing, it is increasing. So this is the anomalous behavior of water, and you should definitely keep this in mind. One or the other subjective question you might encounter, and you should be very specific with what the result is. Now let's move ahead and talk about this very famous equation of time period of a simple pendulum. And I suppose so many of you must be knowing it, because this is a very standard case whenever we are studying SHM. So time period of a simple pendulum, that is 2 pi under root of L by G. It's a very basic case, and all of you must be, if you have ever studied 11th SHM, then you must be knowing about this. So why I am using this equation is because since we are talking about thermal expansion, so length can increase, and in the increment of length, time period should also increase, right? Because time is directly proportional to length. So my main approach is, so suppose I am measuring time using a simple pendulum. So now if temperature changes, its length changes, so the time after which it will make a oscillation will also change, and my entire base is wrong, because for the outside world 1 second should be some amount, and for me now 1 second is altering with the change in temperature. So we need to encounter that. Okay, so what happens is, with the increment in the length because of temperature change, say suppose temperature is increasing or decreasing, whatever is the case, based on that the length will increase, right? The length will increase, and if that change is not in a great amount, I can definitely use the concept of error and its analysis. If you still remember that 2 pi and g are not changing, so t is changing with L to the power 1 by 2. So delta t by t will obviously be equal to 1 by 2 times delta L by L, but mind it very carefully that this should be the case when delta L is not in that significant great amount. If it is occurring in a great amount, then obviously you will have to consider using a different approach, and the approach then will be that you will have to consider an initial time taking 2 pi under root of Li by g, and taking a future time or a final time wherein it will be equal to 2 pi under root of Lf by g. Okay, and then you will have to subtract it, Tf minus Ti divided by Ti, and then after that you can find the relative error or the relative change. Okay, but if I talk about a very small change, so what occurs is, you can just look at this expression. So delta t by t will be equal to 1 by 2 times alpha delta theta. Okay, so now what can be derived from it is, say suppose now delta theta is greater than 0, that means temperature is increasing. So temperature is increasing means length is increasing, length is increasing means time is increasing. So now for a same oscillation, suppose I was using this one oscillation as 1 second to me. Okay, I was using this one oscillation as 1 second to me, and I am located somewhere in Sahara desert or in Thar desert of India, and temperature changes are actually huge. So in winters the temperature can be around or less than 0, and in summers it goes above 40-45. So there are temperature changes, and suppose now summers are entering, so temperature is increasing, my length is increasing, and I have a friend of mine staying somewhere in the coastal region whose temperature variations are not that huge or not that much. So the time period for him, we both have just created a simple pendulum using the same length of wires, same bob mass, and g is obviously same. So entirely we have two identical pendulums, and we measure our time with one oscillation. So now what will occur for me is, my length is increasing and my time is also increasing. So one oscillation now I will consider it to be 1 second, which on the contrary will not be equivalent to 1 second of that person, and obviously for me now time will run slow. Okay, so if delta theta is greater than 0, time will be slow. The 1 second interval over there on a coastal region will not be equivalent to the 1 second interval when I am sitting in Thar. Okay, so I think I am very clear with you people. And if suppose temperature is decreasing, so then also my time will decrease, and now for one oscillation it will be a very quick oscillation. So suppose in a normal sense, if I compare it, earlier the oscillation on a normal scale is 1 second. So now in this case the oscillation time for me will become 1.2 second, and in this case the oscillation time will become around 0.8 second. So now time will be fast for me. For if I am considering every oscillation to be 1 second, then time will be very quick for me and will be very fast for me if delta theta is greater than 0. So suppose you all have understood. So there will be time variations, and this is the concept behind how time will change if you are only using a simple pendulum as your base for time. Okay, so now to you in the chat list or in the comment, just tell me time has been properly framed. Okay, there has been a base on which time has been defined. 1 second has been defined with the help of an atomic clock. So what is the element of that atomic clock? I want your answers in the comment. Tell me what is the material of that atomic clock based on which the standard time, all the time 1 second has been created or understood, and based on it only all the time parameters have been created. Okay, now let's move ahead and talk about specific heat. Yes, that was the topic I was talking about. So what is specific heat? You might encounter terms such as specific heat or molar specific heat, and in thermodynamics they will be greatly used. Okay, so what is specific heat? So if I go by the definition, then it is equal to the heat gained or released by that substance to raise or fall its temperature by 1 degree centigrade for a unit mass of substance. And the definition actually is a mathematical expression only. So specific heat, as you very well know, if it will be dependent upon the change in temperature, it will be dependent upon the mass also, and Q is obviously the amount of heat. So Q upon m del theta will give you the value of S, or Q will obviously be equal to ms delta theta or ms integration d theta. Okay. Now how do I understand that specific heat element? What is specific heat in one way or the other? So say suppose, let me take the case of water. So if I have 1 kg of water, 1 kg of kerosene, 1 kg of glycerine, and 1 kg of so many different liquids, and I impart the same amount of heat energy to all these liquids. So what will occur is, the water will show the least increment in its temperature when I compare it with the other liquids. And the reason to that is the capacity of water to absorb heat, and in accordance with the absorptance and on the absorption, the water is not reflecting that great change in its temperature. That means water has a great storage ability to store heat, and this is the reason why water, so readily available to so many people, is being used in so many nuclear power plants, even thermal power plants, to absorb that excess amount of heat. So some amount of heat is obviously used up in running the turbines and creating steam and moving the turbines, and then thereby generating electricity. But there is a huge amount of water after it is still hot. It is still hot, and there are so many excess heat being generated. So for that, hard water is used, D2O. Okay, and the reason why water is used, because it has great heat capacity, and obviously it's not the best material which we have created, but the other reason is that it's so readily available. Okay, so this was all about specific heat capacity, and always remember, specific heat capacity is related with m. Okay, unlike molar heat capacity, which is related with number of moles. Okay, so molar heat capacity, see, the terms can be different. You might find this molar heat capacity as S in some books, or in some whichever material you are using. So you might find it as C, you might find it as S as well, you might find it as small c or small s as well. But you should be very clear with that whenever there is molar heat capacity, then it is related with moles. So over here, delta Q will always be equal to NC delta T, and this only we will be using in thermodynamics, and stating the molar heat capacities in a process of constant volume, or a process of constant pressure and constant temperature, and so on. And if I talk about specific heat capacity, then delta Q is obviously ms delta T. Okay, so m is the mass. If I change the temperature by delta T, this much amount of energy I will be required. If the temperature decreases, then obviously this much amount of energy will be released, and if this temperature is increasing, then obviously the temperature has to be given to that substance. Based on that only, the temperature variations will occur. Okay, so I suppose you all have understood this case. Now let's talk about heat capacity. So heat capacity in a normal sense, if we just eliminate the presence of temperature, so heat energy can very well be defined as m into C, where C is now a heat capacity. We have just eliminated that temperature term. Okay, so it is the amount of heat required to raise the temperature of a body by 1 degree centigrade. So if the temperature element is not into action, we have just considered that 1 degree is the change in temperature, then the amount of heat energy which will be required. So if we are increasing the temperature by 1 degree, then obviously we will have to give some energy. If we are decreasing the temperature by 1 degree, then obviously energy will be provided to us. It will be an exothermic reaction. Okay, and in such a manner heat capacity has been defined, and you need not to stress upon this. You just need to memorize this molar heat capacity and specific heat capacity, because most of the cases will obviously be regarding that only. And one more heat is about latent heat also, which I will be just discussing in a moment. Now let's talk about water equivalent as well. What is water equivalent? So it is the amount of water which requires the same amount of heat for the same temperature rise as that of object. So say suppose you have water. Obviously I told you water is quite widely used as a heat absorbing element. So things have been defined in terms of water only. So say suppose I am using this substance, and it can absorb this much amount of heat, and in turn will raise the temperature by this much amount. So Nobody is interested in that stuff. Just tell me how much it is related with water, because I have a very readily used and a very readily accepted material, water, which can be used as a heat absorbing element. So tell me in terms of water how it is functioning in terms of water. So this is the options. Suppose both water and that substance are absorbing the same amount of heat. Okay, that same amount of heat delta Q amount of heat दोनों ही absorb कर रहे हैं, एक substance भी और एक water भी. So इसमें जो वाटर इक्विवेलेंट हो जाएगा, डेल्टा टी दोनों का टेम्परेचर ही मान लो सेम चेंज हो रहा है, तो कितना अमाउंट ऑफ वाटर उस चीज़ को रेसिप्रोकेट कर रहा है, दिस इज द एक्सप्रेशन, दिस इज द वाटर इक्विवेलेंट. मतलब इतना मास चाहिए जिसकी हीट कैपेसिटी इतना हो, जब जाके यू कैन क्रिएट एन अमाउंट विच इज इक्वलेंट टू वाटर, उतना ही अमाउंट ऑफ हीट जनरेट करेगा, टेम्परेचर चेंज भी उतना ही रखेगा. ठीक है. सो बोथ ऑफ देयर मासेस डिवाइडेड बाय द स्पेसिफिक हीट कैपेसिटी ऑफ वाटर शुड बी इक्वलेंट. ये चीज़ आप नंबर ऑफ मोल्स से भी कर सकते हो कि नंबर ऑफ मोल्स ऑफ वाटर रिक्वायर्ड, एंड यहाँ पे भी नंबर ऑफ मोल्स ऑफ दैट सब्सटेंस कर सकते हो. सो यू कैन जस्ट चेंज इट अकॉर्डिंगली. ओके, नाउ दिस वॉज लेटेंट हीट which I was talking about. So now suppose you all must have seen that a normal, if I just take the case of water, let me just bring in front of you this graph. So if I just take the case of water, so what happens is, suppose we have 1 kg of ice and the temperature of it is minus 25 degrees centigrade, very obvious, not a big deal. Okay, we have that ice. Now suddenly we take that ice over here and provide some amount of heat energy to it. So we are continuously providing some heat energy to it. Okay, we have placed that ice, suppose in a container, and we have opened our burner which is continuously providing heat energy to it. Okay, this is ice, this is ice, and presently its temperature is what? Minus 25 degrees centigrade. So as soon as start providing it heat, what will happen? This ice temperature will begin to increase. It's not like that, just don't ever feel like that as soon as I provide heat energy some amount of water molecules will turn into water. They will instead, but they will occur, the phase transformation will occur when this entire ice, the temperature of this entire ice is now equal to 0 degrees centigrade. The phase change of ice occurs at 0 degrees centigrade, that's its melting point or freezing point instead, whatever you want to say. So what will happen as I provide, just look at the x-axis. Along x-axis I am actually, this time actually tells me that I am providing a heat energy. So after how much time what will occur, so just consider it that it is the amount of heat energy. So till 1 minute I must have provided some 100 joule of energy, and obviously I am continuously providing. So till at t equal to 2 the energy quotient would have doubled, at t equal to 3 the energy quotient would have tripled. So I am continuously providing heat. So if I am providing the heat, then what happens is, as I am providing the heat, the temperature rises, it rises and it reaches a point at 0 degrees centigrade. This is not 50, it is 0 degrees centigrade. So at 0 what happens is, now also I am providing the energy. So till now what energy did was, it increased the temperature of ice, pretty obvious sir, right? And over here I can very well use this relation that delta Q will be equal to mass of ice into specific heat capacity of ice into delta T. So if the temperature change was occurring say minus 5, so then how much amount of heat energy I had to provide? If I are given with the mass of ice, and obviously specific heat capacity of ice will also be given to me. So depending upon that I can very well calculate the temperature change if I know what amount of heat energy I am providing, or based on the temperature change I can also provide how much amount of heat energy I have provided to that ice. Okay. So during this curve from here till here, this equation will be used. Okay. Now what will occur after that? What will occur after that? So as soon as I reach this position wherein the transformation begins to occur, at this position, now again I am providing the heat, but this heat energy is not changing the temperature of ice now. Instead, it is actually being used by ice to break down its molecules or increase the intermolecular spacing, and instead what should be said in a very clear sense is that entire energy is being used to change the phase of that substance, and change the phase from what? From solid to a liquid. So at this point, this entire AB is actually depicting that this amount of heat energy which you have given in this time interval will entirely be used to change the phase, and it won't go to increase the temperature. Okay, so this entire heat will go in increasing the not increasing the temperature, in changing the phase of that substance, and this kind of a thing you will observe in all the substances. So everybody will have a freezing and a melting point. So at that point, whenever the phase changes, the amount of heat provided will actually be used in changing the phase. Suppose if you just cut the supply of heat energy, then what will occur? Then an equilibrium will be created wherein the amount of ice which has converted into water, it will remain as it is, and the amount of ice which is still remaining, it will remain as it is. So ice and water will neither water will freeze more and neither ice will melt more. Okay, an equilibrium will be created if you are not providing more heat after that. Okay, sir, perfect. And what kind of an equation will be used here? So over here we will be using, say suppose delta Q amount of heat energy is provided, then we very well know that no temperature change is occurring, so that ms delta T function will not work over here. So delta Q over here will be expressed as m into LF. What is LF? It is that latent heat of fusion which I just kept. So here is that latent heat of fusion and it will be equal to Q by m. So let's suppose m amount of ice over here gets melted in the form of water. So how much amount of energy would we have provided? So for m, say suppose 50 gram of ice got converted into water, that means delta Q amount of energy would have been required. Okay. If I want to convert 10 gram or 25 gram of ice into water, then obviously I can very well calculate the amount of energy which should be provided to that ice. Okay. So this kind of a thing occurs over here between point A to B, and once the entire ice has melted into water, then we only have that water kept over here. So now since again we are providing the energy at a constant rate, so now what this energy does is it will do the same function as it had done with ice when it was given to us at minus 25 degrees centigrade. So again the energy provided to water will increase its temperature, and temperature increase will be linear in fashion. Obviously you can very well see the equations. So the delta Q will be equal to m into now S of water into delta T. So now the specific heat capacity will be considered of water, okay, of water, because now the entire substance given to us is of water, no ice is remaining in it, right. So the increment in temperature will obviously be directly proportional to the amount of heat energy given to it. So again the temperature will rise, and this kind of an equation will be used over here, and again 100 degrees centigrade will be reached, and at 100 degrees centigrade what will happen? Again phase change will begin to occur. So again the water molecules will now use that energy to create the spacing between intermolecular, they will just increase the size of intermolecules, and that energy will go over there, and phase change will begin to occur without the increment of temperature. So again this entire process changes, and from C to D the entire chunk of energy which you have provided will be used up in changing the state of liquid to gaseous state. Okay, so now steam will come into picture, and at point D entire water has been converted into steam, and thereafter again with the increment in temperature, with the supply of energy, temperature will rise of steam. Okay, so the reason steam is dangerous than water at 100 degrees centigrade is because of the extra energy which it has. You can very well see that water at 100 degrees centigrade will be at point C, and water at 100 degrees steam, or steam at 100 degree will be at point D, obviously more energetic than water, so obviously it is more dangerous. Although 100 degree water is also not very helpful to you, it will also be dangerous and cause great burns to you, so never ever try these things at home. Okay. Now over here as well, when state change is occurring, similar to the case over here, what kind of an equation will be used? So over here the delta Q will be equal to m into LV. Okay, and what is V? LV is latent heat of vaporization. Okay, so it will be latent heat of vaporization, and even steam's latent heat is given to us, and it is 2268 joule per gram or 540 calorie per gram. Can you understand this? 1 gram of steam, to create 1 gram of steam, 540 calories of amount of heat energy is required, okay, just to create 1 gram of steam. And suppose 1 gram of steam is actually getting converted back to water, then 540 calories of energy it will be releasing, more than the amount of calorie, no, not more than, but significant amount it is, right. 1 gram is actually creating 540 calories. And over here as well, if I talk about the latent heat of fusion, then 1 gram of ice, if it gets converted into water, then this much amount, 79.7 calories of heat energy will be required. On the contrary, if water is getting converted into ice, then it will be releasing 79.7 calories of energy. Okay, okay sir, perfectly understood. So now as we have understood this thing about how energy is getting transmitted and all, let's talk about calorimetry. So what is calorimetry? What is its law? It just says that it is all about mixtures. So suppose there are two substances and both have different temperatures. So suppose it has a temperature TA, it has a temperature TB. Okay, so we have a liquid which is with a temperature TA, and we have a liquid which is at a temperature TB, and we are obviously mixing both of these liquids and creating a bigger liquid with entire mass. So its mass was MA, its mass was MB. So what this law says is the amount of, now let's say TA was at a higher temperature than TB. Let's assume this fact that TA was at a higher temperature than TB. So obviously when we will be mixing both these liquids, TA, since it's higher, so energy will flow from higher temperature to lower temperature, and what will happen after that is an equilibrium temperature will be maintained, which will actually lie between TA and TB. So the temperature over here will be obviously lesser than TA but greater than TB, since TA is greater than TB, and there will be a temperature equilibrium maintained. So the entire liquid will first the energy transfer will occur, some amount of energy will obviously go from here, irrespective of the fact that whether it is 10 gram or it is 1 kg, energy will definitely flow. It will never look at how much amount of quantity you have. If you have 10 gram of this substance and 1 kg of that substance, even energy will flow from this liquid to that liquid, since TA is greater than TB. Now what will be the value of T? What will be the value of T? So I can actually use this result that the amount of energy change will be equal to 0, and what I can do is, let's say suppose it gave an energy, TA gave an energy, because obviously TA is greater than TB. So it gave an energy equivalent to delta Q1, and so it gave an energy, so we will consider it to be negative because the final energy will obviously be lesser than the initial, since it has given energy. And on the contrary, TB, the liquid TB of mass MB will capture energy, obviously, since it has to rise its temperature to a value T. So it will obviously capture some energy, right, Q2. And what I want from you is just ignore these minus and plus sign. Just remember this step, that the amount of energy, the change in energy of TA, that is delta QA, plus the amount of change in energy of delta QB will obviously be equal to 0. So this A and this B, so why it will be 0? Because obviously delta QA is negative and delta QB will be positive, right? Because QB liquid, or the liquid over here in this container B, will have an increment of energy. It will absorb the energy, and what will be its source? Its source will be the liquid at TA, which will obviously be at a higher temperature, so it will be providing that energy to it. And using this result, I can very well calculate the final answer. So what will be the value of final answer? Just tell me. So this A was mixed with B, right? And what I can say is delta QA plus delta QB will be equal to 0. Now let's say the mass of A is MA. So MA into specific heat capacity of A into delta T of A. And what will be the delta T of A? What will be the delta T of A? Change in temperature of A. So initially it had a temperature TA, and finally both the liquids are reaching a state wherein the temperature is T, right? So the change in temperature will be T minus TA. So I need to write T minus TA over here. Okay, and in addition to this, if I want to express delta QB, I can do it in a similar manner. So M of B into specific heat capacity of B into T minus TB, because for B also the final temperature will be T minus TB, and this entire expression will be equal to 0. Now suppose both their masses and specific heat capacity are same, that delta TA will plus delta TB is equal to 0, and this is what written over here. The entire delta T will be equal to 0. But if their masses and specific heat capacities aren't equal, then this entire expression has to be calculated and the final answer has to be noted down. Okay, so this will be all about calorimetry. Now let's solve this question to understand what we actually have studied right now. So what it says is a copper block of mass 80 gram is heated to 100 degrees centigrade and placed on a block of ice at 0 degrees centigrade. Okay, very well, very nice. So what it's saying is a copper block of mass 80 gram is heated to a temperature 100 degree centigrade, nice, and placed on a block of ice at 0 degree centigrade. The specific heat of copper is given to us, the latent heat of ice is also given to us, the amount of ice melted is. Okay, so they haven't mentioned what is the mass of the block of ice provided to us. So there is no mention about the amount of ice which has been provided to us. So what will be a normal assumption then? The normal assumption should be we have very big stretch of ice, okay, we have some big loads of ice kept over here freezed and given to us, and this is the reason they haven't mentioned about ice. If they have mentioned, then we will have to look into an equilibrium temperature, but since they haven't given, so what we will consider is, see, the entire case will be we are given a very big chunk of ice, okay, very big cube ice has been given to us, and an 80 gram, very small 80 gram of copper has been placed over it. Okay, so this ice is obviously at 0 degree centigrade, and this copper of 80 gram mass has a temperature 100 degree centigrade. So what will occur? Definitely all of you must be knowing that heat energy, irrespective of the very small volume of this copper, heat energy will be provided to ice from this point, and the entire amount of heat energy, where it will get used up into. So this ice is at 0 degree centigrade, right, and any extra amount of energy provided to it will change its state. If you remember, it will not increase the temperature, because before increasing, because 0 degree is actually the melting point. So after this point, any amount of energy provided to ice will actually change its state to water. So this is what we need to concern, and since the size of this copper is so small, so what I can say is, when this 80 gram of copper at 100 degree centigrade, when it will provide energy to this ice, so what will occur? Because of this energy, some amount of ice will melt, right, and the temperature of copper will also decrease, right, from 100 to 90 to 80, because it is providing energy, right. With it imparting energy to ice, its temperature will definitely reduce. So its temperature will reduce till a point then no amount of energy has to be given to ice. And when it will occur, we have a big chunk of ice. There is no limitation at all on the amount of ice which we can melt. So obviously one has to sacrifice, that is copper. So its temperature will be reduced from 100 degree centigrade till 0 degree centigrade, and that will be the point when equilibria in temperature has occurred and no amount of heat exchange will occur. So what I actually need to do is, I need to calculate the amount of heat energy which this copper will throw it away or will actually give to ice when its temperature from this point reaches to 0 degree centigrade. Okay, and the amount of energy given by this copper in reaching from 100 to 0 will be the amount of energy used by ice in converting water. So that can be very well calculated using a simple formula. So let's start and just first calculate the amount of energy given by copper. So obviously this will be negative in nature since it is giving energy, so its internal energy is getting decreased. Okay, and the reason is how we can see is because its temperature is decreasing. So what will be the amount of energy given by copper will be, it will be mass of copper into specific heat capacity of copper into the temperature change. So what is mass of copper? Mass of copper is 80 grams, and can I use the value in grams? Yes, because the heat capacity is given to me are in calorie per gram, so I can very well write gram. If they are given in calorie per kg, then you will have to surely convert this gram into kg. Now what is the specific heat capacity of copper? So it is given to us 0.1 calorie per gram, so I can mention 0.1 over here. And what will be the temperature difference? So from 0 degree it will come straight down to 0 degree, and 100 minus 0 will be this much. Okay, final will be 0 and initial will be 100. Okay, final will be 0 minus 100, and as you can very well see, this energy will be negative in nature, and this energy will be absorbed by what? It will be absorbed by ice in melting. So amount of energy absorbed by ice will be delta Q ice. This will be equal to M into LF, right? That's the formula used whenever I talk about state changes, right? So M, let's say M is the amount of ice that is getting melted, and we very well know what is the latent heat of fusion. It is given to us as 80 calorie per gram. So it will be equal to M times 80. And what we need to do, I just need to equate this term over here with this term, right? So 80 gets cancelled, 0.1 into 100 will be equal to 10 gram. And obviously this minus sign, just eliminate this minus sign because it is just indicative of the fact that copper is giving energy and ice is accepting energy. So over here on equating both these statements, you can find the value of M and it will turn out to be 10 gram. And yes, this is the correct answer. So if facing any doubts, any problem, hi Raktim, how are you? So Raktim, are you facing any doubt? You can ask it right away, or just tell me how you are liking the lecture. Have you been understanding what things have been taught over here? And tell me guys. So Arpit, how are you? Study only OP sir. Hi sir, कैसे हो सर? बढ़िया सर. ओके सर, ठीक है. सो देखो ये है आंसर हमारा, ठीक है. और कैलोरीमेट्री में एक बात बताता हूँ मैं. कैलोरीमेट्री में बहुत स्टूडेंट्स को दिक्कत आती है कि सर टेम्परेचर क्या रहेगा, कहाँ पे एक ऑप्टिमम लेवल ऑफ टेम्परेचर आएगा, कहाँ पे एक मीडियोकर लेवल आएगा टेम्परेचर का, कि यहाँ टेम्परेचर मतलब सपोज मैंने यहाँ तो बहुत सिंपल केस नहीं था, बट स्टिल सिंपल केसेस आते हैं कि वाटर ले लिया आपने 70 डिग्री पे एंड एक वाटर ले लिया आपने 10 डिग्री पे, और बताओ कॉमन टेम्परेचर क्या है. दीज आर वेरी सिंपल केसेस, कुछ नहीं करना, बीच का टेम्परेचर टी ले लेना है जो कि मैंने प्रोसेस बताया था आपको, और T-70 T-20 कर लेना, सेम अमाउंट भी रहता है तो आंसर आ जाता है. बट कन्फ्यूजन कहाँ आती है और क्वेश्चन बनाने वाला कहाँ प्रॉब्लम क्रिएट करता है, व्हाट ही विल गिव इट टू यू इज, वो आइस दे देगा और स्टीम दे देगा एंड जस्ट टेल मी what will remain. And यहाँ पे तो the mass of ice wasn't given to us. So now what they'll do is they'll give it to you that 1 kg of ice at minus 20 degrees centigrade is actually mixed with 1.5 kg of steam at 100 degrees centigrade. Now tell me what will be the final structure, कितना क्या बचेगा, मतलब will there be ice, will there be steam, or will there be presence of water? This entire ice will get converted into water, this steam will get converted into water, and also what will be the temperature of that water? So in these questions you might face great amount of difficulty because they are obviously very hectic. पता है बहुत ज़्यादा मैथ्स यूज़ होने करती पड़ती है इसमें. फर्स्ट वी नीड टू कैलकुलेट कि 1.5 kg ऑफ स्टीम अगर 100 डिग्री से वाटर में कन्वर्ट होगा तो कितनी अमाउंट ऑफ एनर्जी रिलीज करेगा. देन वी नीड टू सी कि 1 kg ऑफ आइस को -20 से 100 जीरो करेंगे तो उसमें कितनी अमाउंट ऑफ एनर्जी लगेगी. अगर इसकी ज़्यादा है तो हो भी जाएगा, उसके बाद फिर एक्सेस एनर्जी बचेगी, तो फिर क्या होगा, आइस वाटर में कन्वर्ट होने लग जाएगी. फिर वाटर में क्या इंटायरली कन्वर्ट हो सकती उतनी एनर्जी है वो भी देखना पड़ेगा. सो देयर आर सो मेनी थिंग्स यू नीड टू कंसिडर before proceeding with these questions. So be very specific with calorimetry. Questions can be created in such a fashion and it can actually create very trouble to you guys. So if time doesn't permit, I would personally say to avoid questions if they are so hectic. इतना ज़्यादा अगर transformation देखना पड़े, just avoid them. If you have time, if you have great math skills, you can do that calculations in quick span of time, then you should definitely go for it. I'm not denying the fact that this will actually give you positive marks, but if time is not there, then don't indulge in such type of questions because it will kill a lot amount of your time, and time is the most precious friend over there. Okay my friends, it will be the most precious thing which you will obviously want to save on those 3 hours. Okay, so this is the answer for this question. Now what we are going to do is we are going to take a break and we'll be back in a quick span of time. Till then what you can do, you can just revise the concepts of conduction and just stay ready. थोड़ा ब्रेक ले लो, पानी वानी पियो, get re-energized, and हम तुरंत अभी जाएंगे और वापस आते हैं और हीट ट्रांसफ़र का फर्स्ट मेथड जो है कंडक्शन, उसके बारे में डिस्कस करेंगे. ठीक है, I'll be back in a moment. Bye bye. Okay, hi. So we are again back in the session and हम ये conduction start करने वाले हैं. Am I audible to everyone? Am I audible? Just tell me. Am I audible and visible? Okay, right. चलो ठीक है. So what is conduction? देखो, it normally occurs in solid media. Okay. So this is a very unique type and very common type of conduction method which we have been using quite extensively. Okay. And ये solids में होता है, ठीक है. दो और variant हैं conduction heat transfer के, and they both are convection and radiation. So if I tell you, then radiation is the most common method of heat transfer, which is everywhere. Because of radiation you actually feel that it's hot outside, or your cup of tea, it gets cold after some time. So the reason behind that is radiation, but we'll be discussing about that. First let's get a good idea about what conduction is, and here only I'll be telling you how you can actually memorize your concepts of current electricity, which you already have studied in your 10th class. If you are viewing it in and even most of you who are attending this crash course, they already have studied these concepts in their class 12th as well of current electricity. So we'll be using that concept over here, the entire the process flow and the entire how current is traveling, and current flows when there is a potential difference. Over here there will be a temperature difference, then only heat transfer will occur. So we'll be discussing about all these things, but in this mode of heat transfer, basically what happens is particles of the medium don't move from one place to another. They don't move, they just vibrate, and based on the vibrations get transferred, or in the other case heat get transferred. Okay. So what's the formula behind it? So let's suppose we have a cylindrical rod, okay, and on both the ends of cylindrical rod there's a temperature variation. So over here we have T1 and over here we have T2, and as obvious, you very well know that temperature difference is a must before any heat to flow, and temperature, from a higher temperature to a lower temperature, always heat energy flows. So over here, since T1 is greater than T2, so what I can finally say is that heat energy will flow. Definitely heat energy will flow. So heat energy will flow in a systematic manner over here, and the representation of that I'll very well tell you. So first let's understand what a heat current is. So heat current will be the amount of heat energy flowing through a particular cross sectional area. So dq is what? The amount of heat energy, and through a particular cross sectional area, in this case let's say suppose A. So through a cross sectional area A, in a dt span of time, say suppose 10 joules of energy is traveling or 0.1 joule of energy is traveling, so that element is what? Heat current. So this heat current will definitely depend upon the temperature difference. So more is the amount of temperature difference, more will be the heat current flowing, and if you reduce the temperature difference value, then the heat current will also reduce, and the similarity is just like Ohm's law. So the amount of current flowing in a circuit will be directly proportional to V, right? And the same case will occur over here as well. The amount of temperature difference will decide the amount of heat current which is flowing, and over there, since that proportionality was eliminated by a resistance, here also an element of resistance will come. So what I actually mean to say is that the heat current will be directly proportional to the temperature difference, right? That is T2 minus T1, and there the element of heat resistance was occurring. Here also an element of heat resistance will occur, and this heat resistance is suppose RH into capital H will be equal to delta T. So this entire discussion will be in sync with that only. The terms will be quite differentiated because H is dq by dt, so sometimes dq by dt will be written. So you should be very aware of what heat current is, and in that case also what was current? It was dq by dt, and q over there was charge. So q over here is heat energy. So it is actually, if I tell you the heat current is what? It is the value of power. Rate of change of energy is what? Power. So the dimension of H, heat current, will obviously be power. It will be watt. So now let's move ahead and discuss about what we have just seen. So H will be equal to dq by dt, and how it will be represented. So what you have seen over here, this heat resistance, when it goes over there, so heat will obviously be what we have just written. Heat will be delta T by heat resistance, right? And what was the resistance over there in current electricity? So if you remember, in current electricity, heat resistance was rho L upon A, okay, where rho was the resistivity. So over here also RH will be represented, but not in terms of resistivity or thermal resistance, it will be represented in terms of conductivity. So 1 upon resistivity is what? Conductivity. So this formula can also be written in such a fashion that L upon Ka, okay, L upon Ka, where K is now the current conductivity, the amount of conductivity of a material, but resistivity of a material is better known and given to us. So we don't normally mention conductivity over here, but we can do that. So the same formula will be replaced over here. So this 1 upon R will actually be equal to Ka upon Ka will come over here and dl, right? Okay, so this is the value of R. Now on just replacing this apparatus, this B is equal to IR. Okay, on just evaluating it, what we will finally get is that this is the relation which I am getting. Okay, Tx upon Ka, so it will be R, right? Perfect. So what is R over here? This RH can be replaced by L upon K times A, which we have just spoken about, So now just consider this R in terms of this L upon K, where K is now what? It is your thermal conductivity. Okay, this is your thermal conductivity. A is the cross section area, so it will go above. So delta T into K into A and this L. So now suppose you have a cross section which is of the width dx. So the length now is what? Dx. So this L will be replaced by what? Dx. So dx comes over here. The temperature change across both its ends is now a very small temperature difference, that is dt. So that temperature difference will be replaced by what? Dt. So dt by dx into Ka will be equal to dq by dt. Okay, so this is the expression how it arrived. I have just given you the entire explanation of it. Now one more thing is why this minus sign is arriving, sir. Why this minus sign is arriving? So obviously whenever I talk about heat transfer, so heat transfer occurs from a region of higher temperature to a region of lower temperature. So the final point where the heat energy is going will obviously be at a lesser temperature as compared to the initial point. So final minus initial will obviously be a negative quantity. So in order to make this entire stuff as positive, we provide an extra negative charge or negative value to it. Okay, because this dt which you will be getting, final point temperature minus initial point temperature, this will be negative. So negative will entirely make it to be positive. So heat current will have a proper direction. Okay, so here K is thermal conductivity as obvious, and SI unit of K is watt per meter per Kelvin. Okay, no problem. Thermal conductivity K depends on the material of which the slab is made. Obviously it depends on the material. So suppose if I talk about a metal, so metal will have a very good thermal conductivity, and if I talk about a wood, then obviously wood is not having that amount of thermal conductivity, and this is the reason we have those handles in our cooking utensils made up of wood, because heat doesn't get transmitted from that portion to the end point where we hold it. Okay, so this is the reason, and this is how the entire process will be. So you need to actually construct this entire expression in sync with what you have studied in current electricity, because this will actually help you in all the numericals which you will face. Okay, and I'll be solving questions based on that as well. So in steady state, what I can say is there will be a proper amount of heat flow. That is obviously in steady state, that means the amount of heat energy which is flowing through a particular cross sectional area in dt time is constant for all the elements. So suppose this is the area, this is the area. So a fixed amount of energy is only flowing. The energy is not, say suppose here 5 joule is flowing in 1 second. So here also 5 joule in 1 second should flow, and that is what steady flow is all about. And this formula you very well know, we have just seen that. Okay, and this will be the curve, between T1 and X. So as I move towards this point, this X is like this. Okay, so T1 will be the maximum value of temperature, and as I move forward, the temperature will reduce, and the reduction will be from obviously T1 to T4, that is this point to this point. The rate of increment of temperature with length, will obviously be a straight line curve. Okay, so this entire representation is all about that. Now this I have clearly told you, this is the value of thermal resistance in current electricity. This, yeah, you need to actually make it in sync with that. So we have already discussed that, and now let's talk about series and parallel combination. So this also we have done in class 10th, and even in class 12th in current electricity, that how series resistors in series, what is the value of resistance in that case, and when they are in parallel, so what is the case. So let me recall that. So whenever I talk about a series, the resistance is obviously R1 plus R2, right, and whenever I talk about a parallel connection, then the resistance, net resistance, is obviously equal to 1 upon R1 plus 1 upon R2 and so on for the next term of resistors. So this entire construct, this entire formulation will be same over here as well. Okay, so when I talk about two conductors, not conductors of electricity but conductors of heat, so if they are attached in a series fashion, then their thermal resistances will get add up algebraically as in this fashion, and if they are arranged in a system of parallel connection, then their net result of thermal resistance will be equal to 1 upon thermal resistance of first conductor plus 1 upon thermal resistance of the second conductor, and do remember them. And the next thing is what? You just need to replace R by 1 upon K, L by A, and you will get the final result. Okay. So as in this case, if I talk about a series combination, so as you can see, there is this material with thermal conductivity K1, length L1, thermal conductivity K2, length L2, and thermal conductivity K3, length L3. And obviously this entire apparatus has been placed between 2 points, 2 regions, which are having a temperature difference T1 and T2. So if they are different, then definitely heat energy will flow, and if heat energy is flowing, so I don't need 3 resistors, and I will be not writing 3 resistors. I want a cumulative form, so that in place of that I can just place or consider an imaginary conductor whose resistance I can write it down in a one line expression. So how that will be? It will just be the addition. So R1, as you can see, will be equal to R1 plus R2 plus R3 and this will be the value of R equivalent. So R1 is obviously L1 upon K1 into A, L2 upon K2 into A, and L3 upon K3 into A. Okay, I think it is very much clear. Now if this says that for 2 slabs of equal length, so suppose now the length is same, so how you can actually relate is, if the lengths are same, then I can very well write this expression to be R will be, and only 2 slabs are there. Okay, so R will be equal to L upon K1A plus L upon K2A, and I am just considering a normal conductor whose conductivity is obviously K and length is L. Okay, and say suppose its length is 2L. It's made up of 2L length, here length L and length L, so it's made up of 2L length. So what will happen over here is this L will get cancelled, A will get cancelled, so 2 upon K will be equal to 1 upon K1 plus 1 upon K2. So from this I can very well relate that K will be instead equal to 2 K1 K2 upon K1 plus K2. So the result is derived using that, but that can be very well done by you as well. That's nothing, that's normal mathematics. You just need to remember this concept, and also basically you just need to remember that concept of current electricity, that whenever in series the resistors were added R1 plus R2 plus R3 till Rn, and in parallel, if I talk about a parallel connection, then the addition was 1 upon R will be equal to 1 upon R1 plus 1 upon R2 and so on for the rest of the terms. So as in the case over here as well, so suppose we have 3 different conductors of area A1, A2, A3, and obviously since they are placed between 2 rigid supports, so their length will be same. So it will be 1 upon R1 will be equal to L upon K1 into A1, R2 will be L upon K2 into A2, and over here it will be L upon K3 into A3. Okay, and this will give you the value of resistance 1 upon R, that is the value of effective resistance. Okay, sir, perfect. Now, are there any applications of heat conduction? Yes. So the ice which is getting created in those polar regions, and even if you visit Himalayas, so the Dal Lake in Srinagar, it also gets frozen during the winters, and the reason behind that, or can you just walk over that layer of ice which has been created, or can you just measure the width of that ice? Yes, you can surely do that by using the concept of heat conduction. So the apparatus is same. What happens is, suppose the outside temperature, the atmosphere temperature drastically drops below 0 degree. So what will happen? All the things, all the liquids, basically if I talk specially about water, then water has its freezing point at 0. So any temperature below 0 will actually freeze that excess amount of water which is present around us, right? So rivers cannot escape that fact. So rivers or lakes, normally it doesn't occur in rivers because rivers have a flowing water. So ice never easily gets created over it. But if I talk about a lake which has a very still water, So if the temperature rises to minus theta degree centigrade, then what will happen? The icing or the layer of ice begins to develop from the top and it goes till the bottom. So more you increase this temperature or rather I should say more you decrease this temperature below 0, the more will be the depth of the ice which is being formed. Okay. So this is the case, and obviously the water inside will obviously be 0 because the phase change occurs when the entire liquid is at temperature 0. Before that, if this temperature is not equal to 0, then don't ever imagine that ice will begin to form, because obviously in this same lecture I have told you the phase change occurs when both water and ice are at 0 degree centigrade, and there only this phase change will occur. Okay. So ice begins to form from the surface, and you can actually find the value of dq by dt and all those things using calculus, but that will create a lot of trouble right now. And looking at the time constraints, I have just shown you the exact result which is okay. And questions, mind my terms, questions will ask be only on this thing and this thing, what is the time. So you should just keep this in mind, because they'll be relating, they'll be asking you the ratios, they'll never ask you to find the derivation of it. Okay. So what happens is the rate of formation is actually inversely related to the instantaneous thickness. So more is the thickness, that means less will be the rate of formation of new layer of ice. Okay, so more amount of formation of ice, and apart from that, this dx by dt, that is the rate of formation of ice, the increase in the length of x. So what is x? X is actually the width of the ice which has been created, and if I suppose I want to create a new layer of ice of width dx in a span of dt, so this dx upon dt will be inversely related with the already amount of ice which has been created. Okay, so this is the reason why that entire the entire lake to get frozen up, the temperature should be drastically very much. Okay, because the rate obviously decreases. It decreases as more amount of ice is formed, because obviously heat energy has to first pass through this solid, and after it can enter that space over where on more than that, energy is actually released from this point. Okay. This is at a higher energy, this is 0 degree water, and this is 0 degree or minus theta degree ice. So energy has to flow from this point. Okay. So more is the width, obviously there will be resistance, as you very well know now that heat resistance is directly proportional to L. So more is the length, then more is the heat resistance offered by this ice layer. Okay, and so less amount of heat escapes out, and as a result lesser amount of water will get converted into ice. So all in all, what I mean, what I want from you is you just remember this expression. Okay, and if somebody is asking you about the time taken to deposit x thickness, so suppose x thickness of ice has been created, so there also just remember this expression. More often it will be asked about the relation, how it is depending upon the width. So time taken will be directly proportional to x square, that is the width of the ice which already has been created. Okay. Okay, okay. So time which is being developed, okay, the time to create x thickness of ice is actually directly proportional to its square. Okay. Now let's move ahead and solve this question. Okay, we'll be solving this question with the concepts which we have just learned, and what it says is two identical rods of a metal are welded as shown in figure 1. Okay, so this is probably figure 1. A certain amount of heat flows through them in 16 minutes. So I guess these were the two rods and they were connected over here. Okay, so they are length L and they are length L. Okay, no problem. So the certain amount of heat flows through them in 16 minutes. No problem. If the rods are welded as shown in figure 2, so this is probably figure 2, then the same amount of heat will flow in how much time? We need to find out what will be the value of time. And since they are given as identical rods, that means their lengths are same, their mass are same, and even their thermal conductivity are same. So what I can finally deduce is that the resistance, individual resistance will be same. That means R1 will be equal to R, and that instead will be equal to R2. Yes sir, perfectly fine, perfectly fine. So how I will do it? So the thermal resistance, the net thermal resistance in this case, in case number 1, will be equal to R1 plus R2, and that will instead be 2R. And if I talk about the thermal resistance over here, that is the R equivalent in second case, it will be equal to how much? How much? So I will have to evaluate it by 1 upon R will be equal to 1 upon R1 plus R2, and if the values are same, then the result turns out to be R by 2. You do it yourself. Okay, you do it yourself, you will get the value of resistance to be R by 2. Now the entire apparatus, if you can see, is kept between the same temperature difference. So what we need to find is, we need to find then the same amount of heat will flow in how much time. We need to find the time in which the same amount of heat will flow. So what is the formula? Do you know the formula? Yes sir, we very well know. The formula is delta Q by delta T, that is the value of heat, that will be equal to the change in temperature. Let's say that is delta T divided by the heat resistance. Okay, so this is the formula, right? So now in this case I am concerned with the Q factor, right, that the amount of total heat which is being flowing, and I need to calculate this delta T. Okay, perfectly fine sir. So in this case what we need to do, we just need to divide them, this expression divided by this expression, on both the terms of this case as well and of this case as well. So let's say suppose delta Q1 upon delta T1 is equal to, what is the temperature difference in first case? It will be equal to 100 minus 0, right? So 100 minus 0 divided by, what is the value of heat resistance in this case? In this case, what is the value of heat resistance? It is equivalent to 2R. This will be 2R. Now if I talk about the second case, what is the value of delta Q1 and delta Q2? So I can mention it to be delta Q2. Let's say suppose delta Q2 amount of heat is flowing in delta T2 time, and what is the temperature difference in this case? It is also 100 minus 0. And what is the value of heat resistance? So that we have calculated, it is equal to R by 2, right? We don't have to indulge ourselves in K, A and L, what is the value of thermal resistance. Directly R will work. So since it is given that the same amount of heat will flow, that means delta Q1 and delta Q2 are equal, because same amount of heat is flowing. And also this 2R, R will get cancelled, this 100 minus 0 will get cancelled. So finally what we will be remaining up with, that delta T2 will go upward, delta T1 will come over here, and also over here this R by 2 will go above, so it will be 1 by 4. So what I can finally deduce is just give me a minute. So what I can finally say is that delta T1 or delta T2 by delta T1 from this expression will be equal to 1 by 4, right? Perfectly fine. Delta T2 will go above, delta T1 will come over here, it will go above, so 1 by 2 into 1 by 2, it will be equal to 1 by 4. Now what is the value of delta T1? It is given to us, right? The certain amount of heat, it flows through them in 16 minutes. So we know this time, it is equal to 16 minutes. So 16 will go over there, 16 by 4 is how much? So delta T2 will be equal to 16 by 4, and that is 4 minutes. So is it the right answer? And yes, it is. So now suppose you all have understood. It's a very easy one, and what you just need to do is just analyze it in relation with what all concepts you have studied in current electricity. So how resistances, how current will change, you just have to add on this feature, that here what they were asking about the time period. So that H you need to consider it in terms of delta Q by delta T, and finally you were very clear with the result, what it comes out to be. Let's solve this another question. Okay, and this is also based on conduction. So based on conduction, you might face these many type of questions only. So what it says is 3 rods made of same material and having the same cross sectional area have been joined as shown in figure. Okay. Each rod is of the same length. That means their K is same, their L is same, even their area is same. That means their thermal resistance is same. Okay. The temperatures of free ends are shown in figure. The temperature of the junction will be. So we need to find the temperature at this point, the junction. Let's say the temperature be T. Let's assume that temperature is T. So what I can do is I can create 3 equations out of it. So let's say suppose H amount of heat energy. So the temperatures over there are more. So heat energy will not flow in this fashion, it will flow from this point, and over here it will flow like this. So let's say this heat energy is H1 heat current, this heat current is H2, and this heat current is H3. Okay, so as obvious, H1 plus H2 will have to be equal to H3, right? If 10 joule of energy per second is coming from this side, 10 joule of energy is coming from this side per second, then obviously 20 joules of energy will come out from this side, okay, with this length. So H3, just similar to what electric current was. So H3 will be equal to H1 plus H2. I suppose you all are getting. So the similarity is just like electric current. So H3 will be equal to H1 plus H2, and now we can individually find the values of them. So H3 will be how much? It will be obviously temperature difference divided by the resistance. So temperature difference is Here T is temperature and here it is 0. So it will be T minus 0 divided by what is the heat resistance. So heat resistance is individually same for each of the rods. We can consider them to be R, right? We can consider them to be R. Now if I talk about H1, so what will be the value of heat resistance over here? So it will be final minus 0. If you, what you can do is you can just calculate final minus 0, or you obviously know that this value of T will obviously be greater than 60, sorry, lesser than 60 and 90, but greater than 0. Okay, so well, let's do that thing only. Let's do this thing that final minus 0. So final minus 0, that means 0 minus T. Okay, so 0 minus T over here. Then over here it will be T minus 90. So T minus 90 divided by R. Maths will give us the right answer. We don't have to worry about it. We just need to place it final temperature minus initial temperature plus H2. What will be H2? It will be final temperature, that is T minus 60 divided by its own resistance is also equivalent to R. This R will get cancelled. So finally what you are left with, 0 minus T will be equal to T minus, see 90 and 60 will turn out to be 150, and this T plus T will turn out to be 2T. 3T will go over there, so 3T will be equal to 150, and finally VR with the result of T that will amount to 50 degree. So this is the value of T. This will be the temperature at the junction point, and this is the right answer. If you are facing any doubt, you can ask me right away. Okay, मुझे आपसे subscription लेना है. Okay, so you can obviously subscribe this. Hi Deepak. You can subscribe to the platform and you can definitely study on it. It's free of cost. Just give proper time daily at 5 p.m. Even if you feel that some of your friends might be interested, just share these sessions with them as well. Okay, so what is convection? What is convection? A very normal, very general case. So if I give you an example, then the boiling of milk. Okay, so why cooking is always done from the bottom? Why burners? On burners we place those utensils, use cooking things or what all things in which the cookers and what all utensils on which we cook food basically. So why the heat is supplied from the bottom, and the reason to that is convection. So what happens in convection is that energy is getting transferred in convection as well, but the change or the movement of particles or mediums of the particles actually transfer that energy. So let me give you an example of boiling water. So suppose over here only, if I am boiling this water or any liquid from the bottom, so what will happen? The molecules at the surface, at the bottom of that container will very eagerly and very quickly have their increment in temperature because of the availability of heat energy from the bottom. So what they will do, the layers, the heating occurs in layers. So the bottommost layer will obviously be more temperature or will have more amount of heat, its temperature will be more as compared to the upper layers where heat has not already transferred. So what happens, since its temperature is more, so on increasing temperature you very well know volume increases and density reduces. So what happens in fluids at rest? If a liquid has lesser density, then it will obviously move up, and at the down the liquid with more density will come. So what happens, upon getting heated up by the amount of heat energy being supplied, the layers they just have a reduction in the density, and due to which they move up, and because they are moving up they also transmit the energy to the entire liquid. So in a quick span of time what happens is this entire liquid gets that required temperature which we want. Okay, so over here what happens is there is an effect of gravity also. If gravity wasn't acting in this direction, then the layers, suppose the gravity is acting in upward direction and we are still heating from the bottom. So this case can be understood that suppose somebody is cooking food by providing heat energy from the top. So will he be able to cook that food? Or one more case, I have seen so many people who actually put a bucket of water in summers and they expect that the water will get hot after some time, and that never occurs, because what happens is this upper layer gets heated up, but since this acceleration due to gravity in downward direction, so this layer with less density will obviously remain at that point only, it will not go down. Okay, so that process, and this is the reason why oceans or seas or rivers or lakes, they never have their entire water getting hot during summers. The reason is that only the upper layers get heated up, but the lower layers are still very cold. So if suppose the energy is being provided from the bottom, then obviously waters can have their temperatures increase. So I suppose now you all have understood the effect of convection. It occurs because of the change in density, and obviously materials move just passing on the energy from one point to another. And there is one natural convection which I was just talking about. There is one forced convection as well. So what happens in a forced convection is that suppose you have actually heated up a layer, and now that here layer is not on its own moving on to other portions. So what you will use? You will use a blower, or you'll use a spoon. You will just create disturbance amongst them, and in doing so what happens, the layers which have heated molecules or whose temperature is more will get mixed up with all the layers which are at a lesser temperature and even increase their temperature. So one is the forced convection and another one is the natural convection, and it's very nice that no questions are asked from convection, but you should know of what convection is. It's a very normal thing. Now the third form of heat transfer, first we have studied conduction, second we have also studied that is convection. The third form is radiation. And trust me guys, you all are surrounded by radiation. So a cup of tea, you have just filled up a cup of tea and you just forgot to drink it. So after some time that cup of tea is not at all hot, it becomes cold. The reason is it radiated out the energy to the surroundings. Or why you feel energy, why you feel hotness or coldness, it's because of radiation. You are absorbing energy from the surrounding. Or how sun is actually passing on the energy to all the planets, to earth even, that's radiation. Or how any hot object comes to cools down, or a cool object increases its temperature, why an ice melts. So the reason is radiation. So reason is that this is the most common type of energy, okay, and it doesn't require a medium. It travels through electromagnetic radiations, okay. So what happens is the process by which heat is transferred directly from one body to another without requiring any medium in between is called radiation. So for conduction we required a rod which was actually acting as an agent through which that energy could be passed. In convection we actually had to move the material which was heated up to some other region so that that region can also get heated up. But in radiation, amazingly, we don't even need a medium and the energy transfer is occurring through EM radiations, okay. A perfect, now the case occurs now of black bodies, okay. So what is a black body? And a perfect black body is one which absorbs radiation of all wavelength. Incident on it, its absorptance is unity, and it's neither reflects or transmits any radiation. So this was all about the definition. Now let's talk about a black body first of all. So what is this wavelength? Obviously, as I told you, the heating is occurring because of electromagnetic radiations, and the radiations obviously have a particular wavelength, frequency, and all those properties of waves with it, okay. So what happens is a body, if a body is at a temperature T, if a body is at a temperature T, let's say suppose we talk about sun. So sun has a particular thousands and thousands degree of temperature of its outer crust. So it will definitely emit all the possible radiations starting from 0 nanometer to that infinite value of nanometer, but a particular kind of wavelength will be emitted in abundant quantity, and that parameter we'll also be discussing in a quick span of time, okay, wait for it. But now what a black body does is it has the ability to absorb all the kind of radiations and get heated up, okay. So the reason why so many overhead tanks are also black in color is that black usually absorbs all the colors, it gets heated up also quickly, and it also gets cooled down also quickly. So the suppose actually the coefficient of absorptance and the coefficient of emission is actually unity for it, a black body. So if an object is actually getting heated up quickly, then also it will have an intrinsic property which can state that the amount or the rate at which it will cool down will also be same, okay. जितनी जल्दी वो गर्म होगा उतनी जल्दी वो ठंडा भी होगा, and this is what a black body is. And with the reference of black body, we actually define the absorption or emission of radiations from any other body, of any other body, okay. So how it is done is, let's first deal with what Stephen Boltzmann law is. So what he says is that the amount of heat transfer, and obviously the heat current, amount of heat transfer, the rate of energy transfer, that is dq by dt, will be dependent upon or will be given by sigma EA T to the power 4, where T is actually the temperature of the body, A is its area, the surface area. So suppose I am considering a body whose surface area is A and its temperature is T. So the amount of radiations it will emit will definitely depend on sigma, which is a constant, okay, it's a Boltzmann constant, equivalent to 5.67 into 10 raised to the minus 8, and E is the coefficient of emissivity. Okay, and how it is related or how it is found, I'll be just telling you. So its value ranges from 0 to 1. 1 is when is the value of 1? When we have a perfect black body. So sun is a perfect black body, it is considered as a perfect black body. So when we have a perfect black body, then the value of coefficient of emissivity is equivalent to 1. And for any normal body of any color, of any shape, of any structure, its coefficient will range from 0 to 1. Okay. And the next two terms are obviously area, surface area, and its temperature. Temperature is the most relevant thing over here. So more is the temperature, more will be the amount of radiations, and more is the surface area. That means more ends will be there from which radiations can escape out. So it also directly depends on area. So I want you all to remember this expression, and it actually tells you dq by dt, that is rate of energy transfer. So the rate of energy transfer will be equal to sigma EA T to the power 4 or TB to the power 4, where TB is temperature of the body. Okay, perfect, sir. Now if I talk about the radiation from a body, so this will be the emission. Now a body can also absorb, a body can definitely absorb. So what happens is, a cup of tea, if it is placed at a temperature, let's say suppose we have cooked tea and presently its temperature is around 70 degrees centigrade, and it has been placed in a room whose surroundings are at 30 degrees centigrade. Okay, so what will happen, there will be a radiation from the tea till the surroundings, and there will be a this will be known as emission, and there will be an absorption as well. So absorption will be from the surrounding in the tea, and the amount of energy transfer which will occur, or the change in temperature which will occur, will be a net cumulative result of that. So this expression which you are seeing, the rate of change of energy, this is actually, let's say suppose body's temperature is great, so the amount of energy it will emit out is sigma EA T to the power 4. Now the amount of absorption which it is occurring or which is going on will be also equal to sigma EA, but temperature of surrounding to the power 4. So it is T minus T naught to the power 4, and this will be the actual amount of energy which that material will be having, the net cumulative amount. So there will be a flow of energy on both the directions, from a hotter body to a cooler body and a colder body to a hotter body, but the rate, the more amount of energy radiation will obviously from a hotter to a colder, and that is the reason the temperature of that hotter body will decrease and decrease and decrease till it becomes equivalent to the surrounding. Okay. Now let's talk about Kirchhoff's law. So what is Kirchhoff's law over here as well? So if you remember, Kirchhoff's law was in current electricity as well. So unlike the case over here, also Kirchhoff has given a law, and what it says is the ratio of emissive power to absorption coefficient is same for all bodies at a given temperature and equal to the emissive power of a black body. So this is the coefficient of absorption. Okay, this is the coefficient of absorption, and this is the emissive power. So what you have just seen, that U is what? Its power, rate of change of energy. So the emissive power of any body divided by its coefficient of absorption will be equivalent to the emissive power of a black body. And on just replacing these terms, so for any black body, the value of E is equal to 1. So it turns out to be sigma A T to the power 4. And the emissive power of any body will be equal to sigma EA T to the power 4, and this divided by A will actually give you the value of this. So what it finally tells us, that A is equal to E, and what result we can finally conclude from it is that what I was just telling you, that a good reflector is also a good absorber, that E is equivalent to A. The coefficient of emission is equal to, emissivity is equal to the coefficient of absorptivity. So if I talk about a good emitter, then obviously it is a good absorber as well. So in summers we are told to wear light colored clothes because they are obviously not good absorbers of heat energy, and since they are not good absorbers, they are also not good emitters. So once they are hot, to cool them down you will require a lot amount of time. Okay. And the case with the black overhead tank is, in summers it gets hot very quickly, but it also releases its energy in the night. So the amount of energy change remains same. Okay. E is equal to surface, which is when it is perfectly black. E is equal to 0 when the surface is purely reflective. So null amount of energy it absorbs. It entirely reflects all the radiations falling on it, and its E is equal to 0, and E is between 0 and 1 for any ordinary surface. Okay. So this was all about Stephen Boltzmann law and Kirchhoff law. Now let's talk about Newton's law of cooling. So you can expect a question based on Newton's law of cooling, but Newton already gave this law, but this law has a flaw in it. The flaw is that it will work nicely, it will give you a near to exact result, but only if the temperature ranges, the temperature difference are not more than 40, 50 or 60 degree. If you are going beyond that, if the temperature change between the surrounding and your body is more than 30, 40 degrees centigrade, then exactness will be a bit disturbed when you are using Newton's law of cooling. But in a range of 40, 50, most of you must have been doing so many experiments in school. Presently, during the past 2 years, so many of you must not have got the idea and the opportunity to actually perform experiments. But there's an experiment about Newton's law of cooling, wherein you need to measure the temperature of a hot cold body or a hot water and actually scale it up on a graph, temperature versus time. So at this time, what is the graph, and what you will eventually feel is that the curve turns out to be something like this, a curved one, wherein say suppose the body's temperature was Ti and surrounding temperature is Ts. The case like that only, a hot cup of water or a hot cup of tea with temperature 70 degrees centigrade and the surroundings temperature is 30 degrees centigrade. So what happened, the 70 will definitely decrease, it will decrease, but when it will be equivalent to the surrounding temperature, at that point the amount of heat exchange will amount to 0, okay, and when that will occur, it will occur at a very infinite value. But obviously after this point you will never feel a difference is there in the surrounding and the T's temperature, because it's nearly the same. But if I talk about the exact value when it will become equivalent to that, that's infinity. And how that arises is because Newton said that the rate of decrement of temperature with respect to time, say suppose I had initial temperature Ti, so there will be an decrement in the rate, there will be a decrement in my temperature, right, dt, for a very small interval of time T. The temperature will decrease, and this temperature decrement will be directly proportional to the difference which I have at the present time between surrounding and my own temperature. Now let's suppose it was 70 degrees centigrade and surrounding was obviously 30 degrees centigrade. So now the temperature difference is 40, and till at this moment the rate of heat transfer, the rate of decrement of body's temperature will be very large. So the 70 in a span of just 2 minutes will fall down to 60. But now for the next 10 degrees of centigrade to fall down, you will require more time, that will be 5 minutes or even 6 minutes. So the 70 will reduce to 60 in a span of 2 minutes, and this 60 now will reduce to 50 in a span of, let's say, 5 minutes. So what this actually means is that more is the difference between the temperature of surrounding and the medium, the more will be the rate of decrement of that temperature, and decrement is justified by this negative sign which we have provided, okay. And this is what Newton's law is all about. We will eliminate this proportionality and put in a constant over there, that is k, and finally using what we need to do, we just need to use calculus. So this T minus Ts will come over here, so dt upon T minus Ts will be equal to minus of k dt, and just integrate it from the values from 0 to t, you integrate it from Ti till Tf, and what you will get is natural log T minus Ts and with the limits, and finally you can derive and get to this result, okay. So you need to memorize this result, or on the other hand you can just memorize this result, that is natural log Tf minus Ts divided by Ti minus Ts will be equivalent to minus Kt. Okay, so this is the result which will finally get. This is the final temperature of body. Initially it had Ti. So let's say suppose I have a initial temperature 70, and after some time my temperature reduces to 40, and I want to know the time after which the cup's temperature, the tea's temperature will fall down from 70 to 40 if the surroundings temperature is 30 degrees centigrade. So I can very well calculate the value of time. This constant's value will be given to me, okay. So this is all about Newton's law of cooling. Now let's discuss this very important Wien's displacement law as well, which I was telling you about as well. Now let's say a body has a temperature T1, T2 or T3, whatever it is. So what happens is it emits all sort of radiations. It emits all sort of radiations varying from 0 wavelength till infinite wavelength. But the amount of radiations of 0 wavelength are very less, and the amount of radiations of infinite wavelength are also very less. Basically there is a wavelength which is in the max amount, and that wavelength can be very well understood by Wien's displacement law. So what it said was that the wavelength corresponding to the maximum intensity. Maximum intensity means that is this wavelength was thrown at maximum, means that sun is emitting 100 wavelengths per second or per nanosecond of that wavelength, and the rest wavelengths are lesser than that. Okay, so the maximum intensity wavelength of whichever wavelength, जिस भी wavelength की सबसे ज़्यादा rays emit हुई हैं, okay, so that relation is actually given by Wein's displacement law. So the wavelength with maximum intensity will be inversely proportional to the temperature. So as you increase the temperature, as you can see over here, T3 is greater than T2, which is instead greater than T1. So the wavelength of T1 will be of more value. Okay, as you can see along x-axis wavelength has been plotted. So यहाँ पे wavelength ज़्यादा है as compared to this wavelength because इसका temperature ज़्यादा है. And this will obviously be dependent inversely with time, and exact relation is lambda m is equal to b by t, where b's value is 2.98 या 2.9 into 10 raised to the power minus 3. ठीक है, so you with this relation you can very well know if you have a temperature of any body, you can very well calculate कि सबसे ज़्यादा amount of wavelength कौन सी सबसे ज़्यादा इंटेंसिटी कौन सी वेवलेंथ की आएंगी, सबसे ज़्यादा नंबर ऑफ वेव्स कौन सी वेवलेंथ के करस्पॉन्ड करती हुई आएंगी या एमिट होंगी. ठीक है, so this was all about Wein's displacement. Now let's solve this question. So this question is basically upon Newton's law of cooling. So what it says is a body cools from 70 to 50 degrees centigrade in 20 minutes. Okay, sir, very fine. The time it takes to cool from 50 to 30 degrees centigrade if will be, and it is given that temperature of surrounding is 30 degrees centigrade. Okay, so let's solve it. Should we solve it? No, we shouldn't. Why? Because I clearly told you that the time after which the body's temperature becomes equivalent to the surrounding is infinity. Okay, so with the first look only I should give the answer to be infinity. Okay, because what they're asking me is कि from 70 to 50 it reached in 20 minutes. 70 से 50 जाने में I just require 20 minutes, and now they're asking 50 से 30 जाने में कितना टाइम लगेगा. Okay, they're asking me कि from 50 to 30 how much time will be required, and 30 is given as the surroundings temperature. So 30 degree तो पहुँच ही नहीं पाएगा ना. The graph is like this. The graph is like this. So ये graph x axis पे touch कहाँ करेगा? Infinity पे जाके. तो after infinite amount of time उसका temperature, the body's temperature will be equal to 30 degree centigrade, and before that point it will obviously be very close to body's surrounding temperature but will not be equivalent to that. So पहले स्ट्रोक में मेरा आंसर इन्फिनिटी होना चाहिए. और क्या सही आंसर है? हाँ सर, ये बिल्कुल ही सही आंसर है, इसमें तो चेक करने की ज़रूरत ही नहीं थी. ठीक है, बट इन केस अगर मान लो वो 30 ना बोल के 40 बोल देता, यहाँ पे 30 ना बोल के 40 बोल देता, तो फिर आंसर क्या होता? तो लेट्स डिस्कस दैट. वो सोच लेते हैं, वो डिस्कस कर लेते हैं. ऑप्शन वो नहीं होगा बट वो डिस्कस करके देखते हैं कि क्या होगा. सो नाउ लेट्स से सपोज वो दैट इज कूलिंग फ्रॉम 50 to 40. तो हाउ व्हाट विल बी द अप्रोच ओवर हियर? सो द अप्रोच विल बी, आई टोल्ड यू द फॉर्मूला राइट, दैट ln TF minus TS divided by TI minus TS will be equal to minus of K, and what will be the first time? तो पहला जो हो रहा है, चलो let's write down the formula first and then we'll use it two times. ठीक है. So in the first case what is happening is natural log final temperature is 70, no sorry, final temperature is what? 50 degrees. So 50 minus surrounding is 30 divided by initial was 70 minus 30, and this will be equal to minus of K, and what is the time in which this thing occurs? It was 20. Okay sir, perfect, very nice. Now if I talk about the second case, so in this case they are asking me from 50 to 40, not 30. Okay, 30 का तो infinity है. So in this case what will happen is natural log final temperature is 40 minus 30, that is final temperature of the body minus surrounding temperature, divided by initial temperature was 50 minus 30, and this will be equal to minus of K into time which we don't know. Even we don't know the value of constant K as well. So we need to eliminate that, and that is the reason I have written the expression in such a fashion. If I would have written the expression into e to the power kt, then in that case eliminating that K would have been a very big trouble for me. So writing the expression in this case, now what I can do, I can readily divide both these terms. Okay, I can very readily divide both these terms. So this K will get cancelled by this K, and what will happen over here? So 50 minus 30 is 20, 70 minus 30 is 40. So 20 by 40 will be 1 by 2. So this is natural log 1 by 2. So I can write it to be natural log 1 by 2. Okay, very nice. Now what about this relation? So 40 minus 30 is 10, and 50 minus 30 is 20. So this will be 1 by 20, 1 by 2 even, 10 by 20, that is 1 by 2. So over here also we have natural log 1 by 2. Oh, this is a nice result. So यहाँ से आ जाएगा minus minus will get cancelled, so 20 by t, this will get cancelled, so t is coming out to be 20 minutes. Simple one. This was a simple one. ठीक है. So हमने पता कर लिया कि in 20 minutes the temperature fall will now be from 50 till 40 degrees. So can you people see? मतलब 70 to 50, that is the decrement of 20 degrees centigrade occurred in 20 minutes. And over here the decrement of 10 degrees centigrade occurred in just a span of same 20 minutes only. But the difference was of 10 degrees only. Okay, nice, nice. So this was the entire explanation. Now let's solve this question as well. So what it says is, a liquid in a beaker has temperature theta T at temperature T and theta naught is temperature of surrounding. Then according to Newton's law of cooling, the correct graph between natural log theta minus theta naught and T is. So they are saying theta to be any general temperature. They are not specifying what was the initial temperature, what was the final temperature. So what the result will be over here, if you remember the expression, it was dt upon small dt, that will be equal to minus of k times T minus Ts, right? Place this thing over here, so it now will be dt upon T minus Ts is equal to minus of kt. Integrate both ends. Now the limits are not provided to us. Their limits are not provided to us. They want this general time temperature T only at any temperature T. Okay, so we need to just evaluate it, integrate it, and this is going to be an indefinite integration. So the result will turn out to be natural log T minus Ts will be equal to minus kt plus c, because there will be a constant added in case of indefinite integration. So this is what natural log theta minus theta naught. So theta is this and surrounding is theta naught. And the graph of this versus time. So what will be the graph? So it will be y is equal to minus of mx plus c. So with a positive intercept on y axis, I will have a negative slope. So which of the graphs is like that? Obviously the only one. Looking at the result only, that will be a straight line, so there is only one straight line curve and this will be the result finally. And I suppose you all have understood this lecture. Sir, when will be the first session of JEE Main? Is it from March 20 or not? जल्दी कृष्णा न्यूज़ आ जाएगी, डोंट वरी. अभी आप ये क्वेश्चन पे फोकस करो, आपको टाइम मिल रहा है यार, स्टार्ट करो, ठीक है. इस सेशन को एंजॉय करो, इस सेशन को देखो एंड तुरंत ही न्यूज़ आएगी व्हेन विल बी द फर्स्ट सेशन ऑफ जेईई मेन. ओके, हमें एक्स्ट्रा टाइम मिला है, सो लेट्स यूज़ इट वाइजली, ठीक है. सो दिस विल बी द एंड ऑफ दिस लेक्चर और हम मिलते हैं अगले लेक्चर में. लेकिन तब तक आप लोगों को क्या करना है, व्हाट यू ऑल नीड टू डू, you need to practice questions on app. Okay, you definitely need to do them, and apart from that you need to practice questions and also solve test. Just know where you stand. Practicing questions can be very random. हम 10 मिनट 20 मिनट 1 घंटे में भी 2 क्वेश्चन करते हैं, but that's not the right thing which we should do, because in those 3 hours we won't be given that much amount of time. तो हमें टेस्ट देना पड़ेगा, ठीक है. हमें टेस्ट देके we will have to work on things in a stipulated time. If we'll work on things in the given frame of time, then we can very well know are we performing good or not. So you should definitely download the app. It has a very good interface and you can understand so many things. And we'll be meeting in the next lecture. Remember the date, 4th of Feb, 5 p.m. and the topic will be very beautiful, KTG and thermodynamics. This is a very, very amazing topic. So we'll be seeing and looking at things from so many angles. I'll also tell you the difference, how physics thermodynamics is different from the thermodynamics of chemistry, and how we can actually understand both of them. There's a minor difference in it and we can understand both of them, so no need to worry. If you're having any doubts in thermodynamics, if you have done chemistry also, you can very well attend the lectures. It will definitely have a very good impact. And obviously we'll be talking about so many heat engines, Carnot engines as well in this lecture. So stay tuned. All those who haven't subscribed, subscribe the channel, hit the bell icon for the regular updates. There are so many things offered and created only for you people, जिससे आपका existing knowledge और improve हो सके, ठीक है. हम मिलते हैं next session में. Till then, bye bye, happy learning.